We started a new unit yesterday in dynamics. We defined kinematics earlier this year as the study of motion without regard to what causes the motion. This unit, dynamics, is a study of motion with regard to what causes the motion. What is it exactly that causes motion? One word. Yep. No. Force. Forces cause motion. In other words, we're studying forces in this unit. Now, we're not discounting everything that we learned in the last unit. That's still there, and we'll use some of it sometimes. But the focus is not on the motion itself, this unit. The focus is on the forces that cause the motion. We distinguished between two terms yesterday, one of which we're going to use quite a lot in this unit, one of which we're not. We just want to know the difference between the two. First one was mass. Mass was the amount of matter that's possessed by something, right? The amount of matter that something has. The symbol for mass would be an M, and the units for mass that we use in physics, not chemistry, the units for mass we use in physics is kilograms. Good. Is mass a vector or a scalar? You know that it's a scalar. Good. You know that it's a scalar because when you look at the symbol for mass, it doesn't have a little vector sign over top of it. That's your first indication that it's going to be a scalar. The second thing is a little test you can do, right? Add a south afterwards. My mass is 70 kilograms. South? It doesn't make any sense. So mass is going to be a scalar. There's no direction associated with how heavy I am. Mass is the same everywhere in the universe. It doesn't change. Okay, I go to the moon, I lose weight. I lose 5/6 of my weight. 83% of my weight is gone almost overnight. But if I go to the moon, my mass doesn't change. My mass is still going to be 70 kilograms no matter where I go in the universe. Now, we compare that to volume. Volume, not the amount of matter that something has, but rather the amount of space, yes, the amount of space that something takes up. The symbol for volume would be V, although we're not going to lose sleep over that because we're not actually going to use that in this unit. But it is, it's capital V. The units for volume would be, there's two sets of units you can use for volume. One would be meters cubed, and the other one would be liters. Is volume a vector or a scalar? Yeah, it's a scalar. There's no direction associated with it. We know that on two fronts. One, there's no vector sign over top of the V. And two, wouldn't make any sense to say, I have a 500 ml bottle of water to the south. 500 mils to the south. Makes no sense, right? So it is going to be a scalar. Now, here's the big definition, because this is what we're using in the entire unit, force. Force is defined as, same as it was in grade 6, it's defined as a push or pull, right? It's a push or pull. You push something, you pull something. Wind pushes something, wind pulls something. Anything that pushes or pulls something, that's a force. Now, the symbol for force is F, with the little half arrow over top of it. What are the units? Megan, what are the units for it? Good, newtons. And is force going to be a vector or a scalar? Jenna, force a vector or a scalar? It's going to be a vector, and you know that on two fronts. One, yeah, you get the little arrow over top of it. Good. The second way is, it does make sense to say 28 newtons to the south, right? You apply a force of 28 newtons to the south or 28 newtons to the west or whatever the case may be. Yeah, question? Yes, I did, didn't I? That was just a little test to see if Amelia was paying attention, and she passed. She was paying attention. It is a vector. Correct. Thank you. Good? Do you guys remember the three things that a force can do? The three effects that a force can have? The three changes that a force can make. Force can change what? Yeah. Yes, it can change direction. I think I listed that second yesterday, but it doesn't really matter what order you list them in. A force can change direction. I told you guys yesterday about the time that I was driving my delivery van when I was 17, and I skidded off the off-ramp, right? When I was driving in the off-ramp and going in the turn, the net force caused me to change direction. Okay, I wanted to go in a straight line, but I didn't. I was changing direction. So a force can cause a change in direction. What else can a force change? Yep. It can change the shape, yes. Sometimes we say it deforms an object. It can change the shape of an object. And of course, it can do both, right? It can change the shape and it can change the direction. Or it can do one or the other. Nick, what's the third thing that it can do? Yeah, it can change the velocity or change the speed of an object. It can cause an object to speed up. It can cause an object to slow down. It can cause an object to change direction. It can cause an object to change shape. It can do all three of those things at once. Or it can do one of those three things. But it's got to do at least one of those three things. Even when I push on this wall up here, think like, I'm pushing on the wall up here right now. I'm not causing the wall to speed up or slow down. I'm not causing it to change direction. Am I deforming it? Yeah, I am a little bit. Yeah, not very much, but I am a little bit, right? If you were to take some really precise measuring device that measured the shape of that wall, you would find that that wall is bent a little bit when I push on that wall. So it causes to either change direction, change shape, or change speed, change velocity. Inertia, we defined yesterday as the tendency of an object to, well, we can say to resist a change in motion, or we could just say the tendency of an object to keep doing what it's doing. Inertia is kind of a lazy thing. It's at rest. I can't be bothered. I'll just stay at rest. I'm moving. I can't be bothered doing anything. I'll just keep moving in a straight line at a constant speed. I can't be bothered changing direction or changing speed. Inertia is the tendency to keep doing what it's doing, the tendency to resist a change in motion. What does it depend upon? What is it that causes inertia? The more of this, the more inertia you have. The more mass, right? It depends upon mass. As opposed to momentum, which we're going to focus on a lot in Physics 30, which depends upon mass, and it depends upon velocity. Momentum is how hard it is to stop something, and the more mass it has, the harder it is to stop, but also the more velocity it has, the harder it is to stop. Inertia doesn't depend upon velocity at all. A car sitting in the parking lot has the exact same inertia as a car traveling down the highway. The velocity doesn't affect it. It's difficult to get a car in the parking lot moving. It's difficult to get a car on the highway to speed up or to slow down. It's the exact same value, the exact same amount. Well, then we talked about Newton's first law, which is also known, by the way, as the law of, the law of inertia. An object at rest, what's it going to do? It's going to remain at rest until acted upon by a force. What did I miss? An unbalanced force, right? We have to have an unbalanced force because, listen, you can have an object at rest and push on it with a force. If it's balanced with some other force, it's still not going to move. You don't need a force to cause something that's at rest to move. You need an unbalanced force to cause something that's at rest to move. An object at rest will remain at rest until acted upon by an unbalanced force. What's the second part of that first law? An object, well, what's the opposite of an object at rest? An object in motion. What's an object in motion want to do? Wants to continue in motion in a straight line at the same speed until acted upon by a force, by an unbalanced force. An object in motion will continue in motion straight line until acted upon by an unbalanced force. And finally, equilibrium, which relates to inertia, relates to Newton's first law. Equilibrium we defined as a condition in which all forces acting on the object balance each other out. If you have an object at rest that's in equilibrium, it stays at rest. If you have an object in motion that's in equilibrium, then it's going to stay in motion in a straight line at a constant speed. Remember this, if an object is at rest, it is in equilibrium. Forces must balance. If an object is moving at a constant speed, it is in equilibrium. The forces must balance. Right? Some people think, well, if it's moving at a constant speed, well, then there must be a force positive that's bigger than the negative force. Otherwise, it would slow down. That's not the case at all. If it's moving at a constant speed, it's in equilibrium, the forces balance. Okay, we call that translational equilibrium. If it's moving, we call it static equilibrium if it's at rest. Make sense? All right. Let's go a little bit further with this. Let's define a new term called net force. How many of you guys have a job? Yeah? You get a pay stub every week or every 2 weeks, or sometimes it's every month, depending upon what your job is. Your pay stub lists a whole bunch of stuff on it, right? First thing it lists is what's called your gross pay. Gross pay is the total amount of pay you get from your salary, right? From if you make 15 bucks an hour and you work 20 hours, then your gross pay is $300. Got it? And you also have deductions as well. You're not going to have as many deductions as you do when you're an adult, but you're going to have some deductions still. They're going to take off income tax, perhaps, depending upon how much money you make. Okay, income tax is a negative entry to your pay. You have your gross pay, positive 300. Then they take off, say, $50 income tax, negative 50. And then they take off $20 for, let's say, employment insurance, negative 20. And then they take off $10 for Canada pension, negative 10. And then, because you're such a good worker, they give you a bonus of $30. So now there's another positive $30. When you get to the end of all that on your pay stub, it lists the final amount that's deposited to your bank, and it's called your net pay. You ever see that? Your net pay is your total pay. Your net pay is the pay that you get after you add all of the things that you get or get taken away as positives and negatives. Net force is something similar to that. It's the total force, or it's the sum of all the forces that are acting on an object. All the positives and all the negatives that are acting on the object. If I have a force of 10 newtons to the right and I have a force of 6 newtons to the right, the net force is 16 newtons to the right. 10 newtons to the right and 6 newtons to the left, the net force is 4 newtons to the right. It's the sum of all the forces added up, including all the negatives and the positives. The net force we sometimes also call the unbalanced force. So we could rephrase Newton's first law if we want to say an object at rest remains at rest until acted upon by a net force. It's still okay to say unbalanced force, but we could say acted upon by a net force now if we wanted to. Now, Newton's second law is going to relate to this net force when there is a net force. Newton's first law related to when the net force was zero, right? There was no net force. The unbalanced force was zero. Newton's second law relates to when we have a net force. There is something other than zero. That's going to cause something to happen. It's going to cause an acceleration. It's going to cause the object to either speed up or slow down or change direction. Acceleration. Newton's second law has two parts of it as well. It says the acceleration of an object is directly proportional to the net force. And in the same direction. That means that as the net force doubles, the acceleration doubles. As the net force goes up by a factor of 7, the acceleration goes up by a factor of 7. As net force changes, the acceleration changes in the same direction. Now, the second part of Newton's second law is that the acceleration is inversely proportional to the mass. That means as the mass gets bigger, the acceleration gets smaller. Bigger force, bigger acceleration. Bigger mass, smaller acceleration. That should make some sense to us, right? You get two cars in the parking lot, exactly the same mass. Push one with a force of 10,000 newtons, push one with a force of 20,000 newtons. Which one accelerates more? The one with 20,000 newtons, right? You have two cars in the parking lot, one with a mass of 1,000 kilograms, one with a mass of 1,500 kilograms. Push on them both with the same force. Which one accelerates more? The lighter car, the one with less mass. The bigger the mass, the smaller the acceleration. It's an inverse relationship as opposed to a direct relationship or a linear relationship. Now we're going to restate that mathematically. Newton's second law in words, the law of net, we could call it the law of unbalanced force if we wanted to. versus Newton's first law, which would be the law of balanced forces, right? In first law, we have balanced forces acting, the object remains at rest or remains in motion. In the second law, we have unbalanced forces acting, which causes acceleration. Let's state this mathematically. This second law, this law of unbalanced forces, stated the following way. If acceleration is directly proportional to the net force, then as force gets bigger, acceleration gets bigger. It's inversely proportional to the mass. All right, as mass gets bigger, the acceleration gets smaller. The only way to make that happen is to put F on the top and M on the bottom. So we're going to say that A is equal to F over M. What units do you use for force? This isn't new. What units do we use for force? Newtons, right? What units do we use for mass? What is it? Yeah, kilograms. That means the units for acceleration, we could write it as newtons per kilogram. But of course, we know that we could also write it as meters per second squared. That's the way that we wrote it in Unit 1. Both of those ways are correct. They both mean the same thing. If you have an acceleration due to gravity of 9.81 meters per second squared, that's exactly the same thing as saying 9.81 newtons per kilogram. You get to choose now which way you write it or say it. Just recognize both. And before we do a problem, I want to point out the way that this equation appears on your data sheet. A is equal to F over M. That is Newton's second law. But on your data sheet, it's expressed not as A is equal to F over M, but rather it's expressed in a rearranged form. Take the M up by multiplying, and F becomes equal to M times A. Exactly the same thing. Exactly the same thing. Just rearranged form. Now note as well that we said acceleration was the net force over the mass. I didn't write the little subscript net in here. In this equation, sometimes I will, sometimes I won't. If you see this equation, you assume that that F is the net force, the total force, the unbalanced force. Even if it's not written, you know that it is, in this context, the net force. All right, let's do an example here. Because what is the acceleration of a 20 kilogram box if the net force of 50 newtons is applied on it? This is a pretty straightforward question, right? It's a pretty straightforward Group B question. Remember what I mean by that? A Group B problem is a problem that involves acceleration. This involves acceleration. I'm allowed to use any of the equations that I've learned this year except V equals delta D over delta T. Can't use that because that's Group A. Any of those equations that I learned in Unit 1, A is equal to delta V over delta T, VF squared is equal to VI squared plus 2AD. Any of those, in addition to those, my newest Group B equation, which is F is equal to M times A. Let's write down some givens here and then decide which Group B equation we want to use. My mass is 20 kilograms. My net force is 50.0 newtons. I don't know which direction the net force is in. We're just going to assume the positive direction. Okay, 50 newtons in the positive direction, whatever that is. Solve for A. We're going to say F is equal to M times A. Rearrange that. The M goes down by dividing. I get A is equal to F over M. Or you could have just wrote A is equal to F over M right off the top. I just used the form that's on my data sheet, that's all. F is equal to M times A. Take the force, 50.0 newtons, and we're going to divide that by the mass of 20 kilograms. And that's going to give me 2.5. How many digits should this be? 2.5, 2 digits, or 3 or 4? It matters now, right? It counts now. This is 2, this is 3. Final answer should be 2 digits. Units are meters per second squared. What's the other set of units I could have used? Yep. Good, newtons per kilogram. Now what direction is the acceleration? I don't know. Whatever direction the force is. We assume the force is the positive direction, whatever the way that is. The acceleration is also the positive direction, the same direction as the force, whatever that is. Now, understand here, please understand this. This 50 newtons is the net force. It's not the force, it's the net force. Okay, that means that this 20 kilogram box may be pushed with 50 newtons one way and 0 newtons the other way. Or it could be pushed with 20 newtons one way and 70 newtons the other way. The net force is 50. Or it could be pushed with 1,020 one way and 1,070 the other way. We don't know what the forces are here. Okay, we know what the net force is, the total force. Does that make sense? It's like looking at that pay stub, at the bottom line on that pay stub. We don't know what all those other numbers are when we just look at that bottom line on the pay stub, but we know what the total is. We know what the net is. And that's what we're given in this question. That's what we use with this equation, F is equal to m times a. Does that make sense?